Hi, so this is going to be a quick video about integration in 3D, and I think this is a really handy thing to know a little bit about as you start working with distributions of charge. So I wanted to take a second to talk about it. Um, so to kind of introduce this, imagine first uh, like a rectangular solid, just in Cartesian coordinates, where you'd have something kind of like this. It's in our good old X, Y, and Z, and maybe this is A, B, C. And you could express the volume of this as an integral. So you could break this up into little differential volume elements and add them up, and then you would be able to find the volume. And in this coordinate system, and with a rectangular solid like this, it's really easy to express the volume element as the product of dx, dy, dz. Okay, so imagine like a tiny differential cube. And so this integral over, that we've written over volume becomes an integral over each of these. Dimensions. And in the picture, as I have it, this would be in x, we're going from 0 to a, 0 to b, 0 to c. And so how you can approach this, you can do this one at a time. Now this is basically the simplest example because we don't have, the function that we're integrating is 1. So, but let me just do one dimension just so you kind of see. So this would become x from 0 to a. We haven't integrated over the other dimensions. And you know that that would just pick up a factor of a. Y dz. And notice a is just a constant. It is not a function of y or z, so you could pull it out. And if you of the integral, and if you integrate then over the other dimensions, you would pick up factors for each of those dimensions. And so when you do that same procedure 2 more times, you'd just end up with the product of the 3 lengths, which is what you expect for the volume for, just a little rectangular solid like that. Now, while the differential volume element is very easy to write in Cartesian coordinates, as you're probably coming to realize, we often work with things that are spherical. And finding the volume of a sphere doesn't work very well in that coordinate system. So instead, we work in spherical coordinates. So instead of x, y, and z, we use r, theta, and phi. And let me actually paste a picture that's better than what I'm going to be able to draw. So here's a picture of the spherical coordinate system. And I'll try and point out a few things here. So it's basically, think of on top of your Cartesian coordinate like this. So phi, theta, r, this is r. And, these have unit vectors too. Like oftentimes in electrostatic product, in problems and stuff, you work with things that are pointed radially, well, that would be the unit vector associated with r. And so r is here. So it's pointing like this. So the thing that I want to point out is notice this little depiction here of the volume element. So the volume element is more complicated in spherical coordinates. There's going to be, in r, there's a factor of dr. But in the theta, or in the phi direction, notice it goes like r d phi. So imagine like a little arc length of r d phi. So let me actually write these separately. R d phi. So that's, this piece. And then in addition, there's this r sine phi d theta. So in the theta direction, there's a factor of r, but there's also this sine phi projection. And you can think of that as accounting for, think of like how lines of longitude converge at the poles. It's a way of accounting for that, the fact that they're not equally spaced. You have to have that projection of phi. So so if we want to find the volume of a sphere, for example, it's the same kind of conceptually, it's the same thing. The volume will be the integral of dv, but it's become a little more complicated. So we have 3 variables, so it'll be a 3-dimensional integral. But now we're integrating, and we can kind of consolidate some of this. We'll have r squared. I'll write it as r squared sine phi d theta d phi dr. And theta, you can see in this picture, it's going to go all the way around. So this one is from 0 to 2 pi. Our phi integration, it only goes from like the North Pole to the South Pole, so that will be from 0 to pi. And our r integration, let's call it from 0 to big R, where that's the actual outer dimension of your sphere. So let's integrate this. If we look at the theta piece first, notice there isn't anything in here that depends on theta, so the function of theta is 1. So it's the same. We would just pick up, I'll be real explicit about it, but we would pick up theta from 0 to 2 pi. We still have everything else in here. Okay, so and that would give you a factor of 2 pi. Okay, and then notice now we have sine phi. Integrate that part next. So what's the integral of sine? It'll be cosine, negative cosine. So we're going to evaluate that from 0 to pi. Just kind of stick it in here. And we still have our r squared and contribution. Now notice this, so it's negative, so we would have cosine of, so what does this equal? This would be negative negative 1 minus negative negative 1 again, minus 1. So this would be equal to 2. So we pick up another factor of 2 from this. And then we have just our R integration left. So, and that's just R squared. So if we integrate that, you're going to pick up R cubed over 3. So you know what we're looking for here, but I just wanted to show you. And you plug in your limits and you recover the volume of a sphere as you expect. Now, this might seem like, wow, that's kind of lame, but why I bring this up is because there are problems that appear in your homework where you need to find like the total charge on some spherical distribution. So, and some of these are really simple because it'll just be some volume density. So this is just the charge per volume. I don't know, I'll put volume. And if this is a constant, this is really simple because when you go to add this up, what is it? Well, you could integrate this over volume. But this is a constant, so it doesn't depend on r theta or phi. So you could pull it out. You pick up, the integral of that. Assuming this is a sphere, you would then just get rho times the volume. This thing has radius r. So that's no big deal. You're just multiplying the volume times the density. But where it gets interesting is what if this rho depends on r? So, and in principle, it could depend on the angle as well. But suppose instead you have a rho that is a function of r. So for example, maybe it's got some initial value in the center, and then it drops off like this. Okay. Actually, not assume. Consider this. So you can see how this behaves. As a function of r, instead of just being constant, it's got a value of rho naught in the center, and then it's got a value of 0 at r equals r, so in other words, at the surface. And so note, this wouldn't be a conductor because all the charge on a conductor would be is going to reside on the surface, but you could have some kind of dielectric where charge is distributed. And in this fashion. So in other words, it's concentrated at the center. This is R, and this is the density. So in order to find the total charge, you're going to need to integrate this expression. So let's do that. So you'd have to integrate your rho as a function of R over the volume. And we would want to expand this into our full picture. So don't worry. I mean, the angle parts of this will go away right away, but we'll just include them just so we kind of have the whole picture. So again, this is assuming we have some, sphere of radius r that has this dependence on the charge distribution. So this thing would be inside our integral, and our differential volume element, remember we need that, our r squared sine phi theta d phi dr. Now let's do ourselves a favor and break this in two. So we have this this difference, um, and so on the one chunk we'll have uh, really it's just the rho naught times, there's a 1 there, I guess, integrated over the volume. So what is that? That's just rho naught times what we already found. That would correspond to sort of the contribution if the thing had just constant density. And then in addition to that, we're going to subtract, or not in addition, we're going to subtract from that this piece. So where we have the part that depends on R. And so there's a R over big R. And actually, I can pull this, pull out the R naught, or the rho naught. Work through these. So actually, let me just move this down a little bit. So notice the angle pieces, this function does not depend on theta or phi. It's spherically symmetrical. So we would pick up our same 4 pi factor from the angular pieces. And then this would become an integral of r cubed over big R. So that's the constant as well, but I'll leave it there for now. And what does that equal? Well, we would have r to the fourth over 4. So I'll do it step by step here. R to the fourth over 4. We still have our factor of r evaluated from 0 to big R. We still have our other chunk there. So this would give us put our limit in. Notice we have r to the fourth over big R, so we would lose that factor. We'd have 4 pi rho naught over 4 r cubed. So there's a lot of commonalities, or common pieces in here. Really everything is the same. Rho naught 4 pi r cubed. We have, actually, let me do like this. Simplifying this here. We'll just leave the numerical factor. 4/3 minus 1. So this becomes rho pi r cubed over 3. And that would be the charge inside this sphere of radius r that has this charge distribution that goes like 1 minus r over big R. And this should hopefully be of use to you as you start working with these spherically symmetrical things, just to see an example of how you can integrate over the sphere, see where the volume of a sphere comes from, and that sort of thing. So.